Hi everyone, welcome to lecture 5 on CaPow. This is part 2, which is about power analysis for study design and model exploration. So in part 1 we covered a lot of ground. There was an introduction to CaPow. We looked at model fitting for existing data using the Maui Dolphin example dataset. And I tried to explain the concept of statistical power analysis using simulation, and we're going to be looking at that in more detail in this part. And then I talked a lot about the diagnostics that we need to do when we're performing a power analysis by simulation. And we looked at those diagnostics for an example, which I'm calling the first study design example. And I realized that we finished with the diagnostics for this example, but we never actually got on to the power analysis. So that's where I'm going to start today. So yeah, I'll show you that. So coming back to CaPow and just looking at our projects, we've got our study design example 1 project, which we described as having surveys from 2001 to 2003 and 2009 to 2011. And I'll actually just show you again in the Sim Builder module. You can view all of the sims that you've built and saved using the View Sims tab here. And so we can see the simulation that we used for this project. So remember, we found the superpopulation size we needed was 742. We had our 3 surveys at the start and 3 surveys at the end of the study. And we had survival probability of 0.95 throughout the study. Capture probabilities were constant at 0.1. And the growth rate lambda was 1.03. Then the entry proportions are calculated from lambda and phi. And we've got our expected population sizes calculated from entry proportions and the superpopulation size. And remember that we wanted an initial population size of 400. And so it's growing at 1.03. Factor of 1.03 per year throughout the study. And so we looked at all our diagnostics, and mostly they looked fine. Remember, there was one thing that we were concerned about, which was that we had some boundary estimates for the survival probability. And it looks like in about 100 of the 1,000 simulations. So not a massive failure, but something that we definitely need to take note of and need to include in our analysis of this power analysis. Now, so I'm on the confidence interval plots, and well, I'll show you the power analysis module now. So we've looked at our diagnostics for this power analysis, for these simulations, and we've decided that they're not too bad, looking pretty good. So we can have a look at the power analysis module. And you can see I've already chosen the right settings here. So the parameter that we're interested in is lambda. And the value, the test value that we're interested in is 1. So what this corresponds to is the value of lambda at which the population is not changing, right? If lambda is 1, then the population is constant throughout. And so if we're asking in our power analysis if lambda is different from 1, so if we can exclude the value 1 from our power, from our confidence interval, then we're able to tell whether the population is increasing or decreasing, right? If lambda equals 1 is inside our confidence intervals, then we cannot tell at that level of statistical significance whether the population is increasing or decreasing. And the level of statistical significance that we were interested in was 0.95, so a common level of significance there. So I've got those settings chosen, and I've selected the study design project, and then I can hit the power display button. And so, well, first of all, you can see this plot here, which I wanted to point out that this is exactly the same as the confidence interval plot for lambda. So these are all of the confidence intervals that were calculated for all of the simulations in the study. And remember, the gray dots are our estimates. The dots above and below are the confidence intervals. And now the difference in the power module is that we have a solid blue line at the value of the parameter that we're interested in testing against. So we're testing against lambda equals 1. And so we have a blue line at lambda equals 1. And then the color of the confidence intervals is changing when the test value is not included in the confidence interval. Right, so that's what we're talking about when we're asking about the power of a study. So you can see that the black dots look like a bit more than half of the confidence intervals. And that's what we're getting reported here for the overall power of this study. So we've got an overall power of 53%. And what that's saying is that 53% of the confidence intervals that were calculated exclude the value of lambda equals 1. And in this case, we actually have all of those confidence intervals are above the value of lambda equals 1. So we could also have confidence intervals that were down below lambda equals 1, but also excluded that value. And so those would also be a part of the power of the study. But in this case, our estimates never get that low. So all of our confidence intervals that exclude lambda equals 1 are above that value of lambda. And that's not surprising because remember the true value of lambda is 1.03 in this in our simulations. So it's not surprising that we're estimating lambda greater than 1 most of the time. So power analysis for study design. Why would we do power analysis? What does it mean to us? Well, if you're designing a capture-recapture study that could cost millions of dollars and take decades to complete, you'd like to know if the study would tell you what you want to know. And so in this example, we're talking about whether the population size is increasing or decreasing over time. And as I explained, if lambda equals 1 is included in our confidence intervals, then we can't say whether whether the population size is increasing or decreasing at that significance level. So if we simulate our study 1,000 times, and 90% of the time lambda equals 1 is included in our confidence intervals, then the probability is 0.9 that the study will not tell us whether the population is increasing or decreasing. So that would be a bad thing, right? But we might be able to change our study design so that we can get more power. And we would like to do that before we go out and spend millions of dollars on the study. So if you think about the example that we just did in CaPow, the power was 53%. So I guess that's not bad, but we might like to try a different study design and see if we can do better. So you've seen one example of doing a power analysis in CaPow, but just to go over what the process is again, you're basically just simulating a lot of data sets and then fitting the same model to all of them. And the way you do it in CaPow is you build the model and build the simulation. You combine the model and the simulation into a project, and then you run the project and you can specify how many times to run that simulation. And we usually choose about 1,000. Then you check the plots and summaries for all your diagnostics, so checking for bias and confidence interval coverage and boundary estimate. And if all of those look okay, then you would check the power in the power module. Okay, so this is the slide with the study design example again. And what I actually want to do is compare two different possible study designs. So both of them have 6 surveys. We've just done the first one where we had surveys in 2001 to 2003 and 2009 to 2011. And now I want to compare that study design with a different study where the surveys are spread evenly throughout the period of the study. So surveys every 2 years, 2001, 2003, 2005, 2007, 2009, and 2011. So it's the same number of surveys, they're just spread out evenly instead of lumped together at the start and the end. And again, we're just assuming the same values of the parameters. Initial population size of 400, lambda equals 1.03, phi is 0.95, and capture probability is 0.1. And so I want to compare this new study design in the same scenario and see if it gives more or less power to detect if lambda is not equal to 1. So to exclude lambda equals 1 at the 95% significance level. So you might like to just pause the video now and ask yourself which of these two study designs you think will give greater power. So I'm going to go back to CaPow now. And so we will be fitting the same model to this new study. Well, that's not right. So the difference in the model will just be that the surveys are at different times. Right, so I still have my information here from the first study design. I'll just change the model name to example 2. And the survey is now 2001, 2003, 2005, 2007, 9, and 11. And I'll change them in the matrix. And then we're still fitting a pop and lambda model, estimating the superpopulation size, lambda and phi, starting at 2001. And we're assuming constant capture probabilities. So I'll save that model. And then I'll need to build the new simulation. Okay, and now you can see that the expected population size, initial population size has changed because we've got different surveys now. So I need to go back to the NS calculator tab and put in my parameter values. and my surveys. Okay, and you can see that for the same initial population size and the same parameter values, but with different surveys, I'll need a different superpopulation size to get to match those values. And the reason is when you're doing the surveys at different times, different numbers of animals are going to be exposed to capture. So when you have a large gap between the early surveys and the latest surveys, as we did in the first study, more animals are going to be born and actually die between those middle surveys and never be exposed to capture, so they won't actually be included in the superpopulation. So we're going to put this superpopulation size of 757 into our simulation, and you can see that that gives us the correct initial population size of 400. So I'm saving that now. And now I'm going to create the new project. And choose the new simulation and the new model. So there's my new project. And now I'm going to run it for 1000 simulations. Okay, and let's look at the plots and summaries. You should always be careful when you're plotting in CaPow to make sure that you select your project. If you don't select the project and you try to plot, you can crash the app. So that's one of the, unfortunately, one of the bugs I haven't had time to fix yet. Okay, and I'll change the settings to have 2 plots per column, and I'll make the height larger. Oh, that's too large. That looks good. And I'll just make the text size a little larger. Okay. So let's start with the box plots. So looking at the mean estimate and the true value of the superpopulation size, again, they're pretty close, which is good. It looks like not much bias there. And the box plot has a nice spread around the true value. Same looking at the growth rate lambda. That looks good. Again, we have this solid blue line at the top of the plot for the survival probability, showing that we got some boundary estimates again. But again, the box plot doesn't look too bad apart from that. For capture probability, it looks like we got a boundary estimate sometimes, but probably pretty rarely. And the box plot looks good. And for entry proportions, again, some boundary estimates for the first entry proportion, but the box plots mostly look good. And remember, these are a different color because they're being calculated from lambda and the survival probability. So they were not just estimated directly. So it doesn't look like much problems with bias, but we can have a look at the mean plots. And straight away we can see that this one looks like the worst one, and that's for capture probability. But remember, we need to check the scale of the axis, and again the scale here is very small, so even though that looks like a lot of bias, it actually only corresponds to about 0.005 difference from the true value of the capture probability. So that doesn't look too bad. Looking at the confidence interval plots, for the superpopulation size, the confidence interval coverage is good, and we don't see any problems with boundary estimates. Same for the plot for lambda. Confidence interval coverage is perfect. For phi, we have the same sort of problem here. So we've got boundary estimates in about 200 of the simulations this time, where the survival probability has been estimated to be 1, just the upper limit. So that's not too good, and in fact, it seems to be a little worse than in the first study design, because it looks like there's about 200 rather than only about 100 in the last design. So that's not too good. And for capture probability, it's looking good. No problem with confidence interval coverage, and no boundary estimates. Looking at the summary table, confidence interval coverage again is good, and really this is just for getting a lot more detail if we need it. So let's look at the power analysis tab, and you'll get an error like this when you haven't selected one of the projects. So we'll select Study Design 2. And so the power now has been reduced. So we can actually look at both of these studies together, and I'll just make the plots a little bigger. So remember, in the first design we had a power of 53%, and in the second design now we have a lower power actually, 38%. And you can see that so whereas most of the confidence intervals were above, excluding lambda equals 1 in the first study design, now it's not so many. And so it's a pretty subtle difference if you look at the estimates. But it looks like the estimates of lambda are maybe just a little bit lower in general. And the confidence intervals may actually be a little bit wider. And we can actually try looking in the summary tables again and comparing for the two study designs. What was the average confidence interval width for lambda? So in the first study it was 0.06, and in the second study 0.07. The mean estimate for lambda in both cases was the true value, 1.03. So the main difference does seem to be that the confidence interval width is larger for the second study. And so what that means is that it's got less precision. There's no problem with bias, no difference in bias between the two studies. The difference is that the second study just has less statistical power. It has larger confidence interval width, so more variance in the estimating. So to answer our question now, and you can think about what you guessed, it turns out that the study with the surveys lumped together at the start and the end of the study gave more power about our estimate of lambda than the study with the surveys spread out throughout the study period. This is just explaining what I showed you with the NS calculator. Okay, so why would it be that a study with all of the surveys lumped towards the start and the end of the study period would give us stronger, more statistical power in our estimate of lambda? Well, when you're fitting a pop and lambda model, you're assuming that the population growth rate lambda is constant throughout the study. And so what that is saying is that the population is following a smooth exponential curve. And so this is like a kind of linear regression. We're fitting a smooth exponential curve to the population size over the period of the study. And if you have studied linear regression, you might remember that when you have data at the beginning and the end of your range, that information has more leverage over the line that you're fitting. And so when you have a study with more surveys at the beginning and the end of the period, those surveys have more leverage over the population growth curve that you're fitting to your population size. So I think that's an intuitive way of understanding why those studies will give you more power over your population growth rate lambda, more power to estimate it more accurate, with more precision.